2026, question number 4. So only 5 questions on this year's paper, and this being worth 26 marks represents almost a third of the entire paper. So this is going to cover quite a lot of material, and it's going to be quite a long one. This is also going to be the main organic chemistry that we're going to see. We did see a little bit of organic chemistry in question number 3, but this is going to be your synthetic roots question, although there's not really much organic synthesis for the diehards, I'm afraid. So write the molecular formula for beta carotene. I'm not gonna go through how to do that. You just need to, make sure you're getting it right yourself. But that is the correct molecular formula. Just have a go. If you don't get the right numbers, try it again. See which hydrogens you missed. Then we have the colours come from the alternating chain of carbon-carbon double with carbon-carbon single bonds. We're given alpha carotene and asked to find the number of conjugated double bonds in alpha carotene and in beta carotene. So if we look at alpha carotene, this double bond here is not part of the conjugated chain because it's double, single, single, double, which isn't going to work. Okay, it needs to be double, single, double, single, double, single. So this one here isn't part of the conjugation. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, which are all conjugated. And then beta carotene, you can see that this double bond here now switches over to here. So now this is part of the conjugation. So we have 11 conjugated double bonds. Then we have this really rather interesting molecular orbital question. I was very pleased to see this question. This is something that a part of chemistry that I'm really into. So it was nice that this has come up this year. And we have the idea of molecular orbitals being formed from the overlap of p orbitals, sorry. So the overlap of the p orbitals gives you a pi orbital, which is something you should be familiar from your studies. But when you got taught at school, you were told that p orbitals overlap side on to give you a pi orbital. Probably what you weren't told is that we can do this different combinations of the same orbitals. So because we have a positive value here and a negative value here, that's the wave function, which is a little bit complicated. Don't get confused and think that there's one electron up here and there's one electron down here. That's not what this means. This is treating the electron as a wave, just like if you had, let's say for example, a standing wave or like a string on a guitar. Then the wave would look like that, and over here the function has a positive value, and over here the function has a negative value. That's the same thing. It doesn't really have any physical meaning. It just is positive here and negative here. Just like you could say, if you had this standing wave on a guitar string, this bit here is positive, this bit here is negative. It doesn't really have any physical meaning in terms of the sound that the guitar is making or anything like that. So the combination can be constructive and it can be destructive. Now, if it's constructive, we're going to get our standard p orbital, right, which is going to be a bonding interaction because the electrons are going to be between the two atoms. Whereas if we have this destructive interference here, what's going to happen is that they're going to sort of cancel each other out in the middle here, and so you're going to be left with this bit up here and that bit there of the opposite sign, and then this bit down here and this bit here of the opposite sign, and you can see the electron density is on the outside of the nuclei, so it's going to be pulling the electrons away. So this is a bonding orbital, a bonding molecular orbital. This is an anti-bonding molecular orbital. It's a very, very brief explanation of molecular orbital theory. If you're interested, go and look up a little bit about MO theory. But the key thing here, in order to be able to answer this question, is that you need to be able to identify that when you're given a constructive interference, a bonding interaction, that's going to be lower in energy. So if you have this orbital and you have this orbital, the electrons will go into this orbital because they are lower in energy. So we're given these 4 orbitals here, and we're asked to put them in order of energy. What a lot of students that I saw did was they just had the order wrong. So they realised that there was an order, but they weren't quite sure whether it was this one was the lowest energy or it was this one that was the lowest energy. So more overlap, lower energy. And you can see that what's happening is, if we think about it in terms of a wave, you have this sort of, that is all constructive, so it just becomes all a positive wave. Whereas here, we've got this point here where it changes sign. So the positive part is up here, then the positive part is down here. So it's going to give you a wave that looks like that. Here, that's going to happen twice, so it's going to look like this. And here it happens 3 times. Okay, so this is obviously a higher energy wave than this wave, because this has got a higher frequency, shorter wavelength, if you will. So we know that this is going to be the lowest energy. So I can go ahead and just write in my lowest energy is B, then A, then D, then C. Okay, and then you're given this hexatriene, and I mean, this is really the thing about this question that I wasn't really sure about, is that if you get this concept, it's basically just 5 free marks. This isn't really that difficult, and so if you've clued into the fact that the more overlap there is, the lower energy is, it's basically just 5 marks. Okay, so this one, they are all the same. Put those in like that, and then this one you're going to have 1 node where the wave function changes sign. This one you're going to have 2 nodes where the wave function changes sign. This one you'll have 3 nodes, so that's 1 node. So you must have 1 over here due to symmetry, and then you have 1 in the middle. So like that, that's 3 nodes. So now I must have 4 nodes. This is, I think people quite often, if they got everything right, except for one thing, it was one of these 2. They weren't quite sure which way around these ones went. But that's 1, 2, 3. So I need to have 4 nodes in this one, like that. And then the top one, 5 nodes, so where they're all different, all 6 are different. Like that. Okay. Now, we are then asked to calculate the energy gap in hexatriene. Okay. Again, if you want to read the question, just pause the video, give it a quick read. I'm not going to do that. I'm just going to get straight on. So we have 4 beta sine 90 over n plus 1, where n is the number of p orbitals in the conjugated system. So for us, n is going to be equal to 6, and beta we're given here. So I'm just going to go ahead and do that calculation. So delta E equals 4 times 6.85 times 10 to the minus 19, which is my value of beta multiplied by sine 90 over 7. Okay, double check first that my calculator is in degrees. It is, so which is lucky because I don't have to change it. Do that, do the sine of that, multiply by 4, multiply by 6.85 minus 19. Gives me 6.1 times 10 to the minus 19. Now the Olympiad, the instructions for when we grade the Olympiad is that we should penalise once per question if the student doesn't include units. So here, if you didn't put units, then there's only 1 mark. It means you don't get the mark because in the question you're told to calculate the energy. It doesn't tell you what units to put the energy in, so you have to include units with it. Now, obviously, this angle part is not going to have any units, and beta is given in joules, so it's very simple. No reason to miss that bit out. Then, calculate the wavelength of light absorbed by hexatriene. This, it's been a while since I taught A-level. I don't remember this being on the A-level specifications. It's in the, if you do the IB, this is a standard IB calculation where you have to convert an energy into a wavelength of light. So, in fact, as well, the data sheet that you get with the Olympiad paper even gives you E equals HC over lambda. Normally, you'd be given E equals HF and C equals F lambda, and asked to combine these into this form to do the calculation, but very generously they've given you the combined version. So we can just go ahead, put the energy gap in, 6.1 times 10 to the power of minus 19 equals to our Planck's constant, 6.626 times 10 to the minus 34, multiplied by the speed of light, 2.998 times 10 to the power of 8 divided by lambda. And then I just solve for lambda. So lambda is going to be, that's my energy, so I'm going to divide it by 6.626 times 10 to the minus 34, and I'm going to divide it by 2.998 times 10 to the power of 8, which gives me that. Now what I've done is I've sort of taken this number, divided it by that, but this is still, the lambda is still down here, so this is actually 1 divided by lambda. So I actually take the reciprocal of that number to give me my wavelength. The speed of light here is given in meters per second, so my answer has come out in meters. The question does specify to give your answer in nanometers. You will not get the mark if you don't put it into nanometers. So I can see here, this is 1, 2, 3, 4, 5, 6, 7. So let me write that out. All right, 3.26 times 10 to the power of minus 7 meters, which I know is going to be 326 nanometers. Now, obviously you should know that 1 meter is 10 to the power of 9 nanometers. But in general, this is a very common unit conversion to go from 10 to the minus 7 meters to hundreds of nanometers. You know, as soon as you see 10 to the minus 7 meters, you should be thinking, well, it's going to be that hundreds of nanometers. And the reason that's a common unit conversion is because this is the hundreds of nanometers is the wavelength of visible light, where that region falls in. So it's just a good thing to just be aware of. And then we're actually told visible light has wavelengths between 380 nanometers and 720 nanometers. Okay. Based on your answer to E part 2, tick the answer in the booklet whether hexatrine absorbs visible light or not. No. The easiest question I think there'll be. So just so we're clear, what's happening is that the energy gap here that we've used, this energy gap is, sort of represent it here, this energy gap, which is 6.1 times 10 to the minus 19 joules. What happens is the electron, if you shine light on the electron will move up from the lower energy level to the higher energy level. And the energy of the photon has to be equal to the energy gap. So all we're doing is we're converting the energy of the photon to the wavelength of the light that is shining on it. In the answer booklet, tick what happens to the wavelength of light absorbed as the number of conjugated CC bonds increases. So if the value of n goes up, then this angle gets smaller, which means that the energy gap gets smaller. So if I've got a smaller energy gap, that means that the light coming in to do the transition between the energy levels must be lower energy. And lower energy light is going to have a larger wavelength. So it's always very, very important that you are aware of how the energy, the frequency and the wavelength of light are related to each other. So smaller energy gap, lower frequency, longer wavelength. Okay, which can be a little bit confusing because this number's getting smaller, this number's getting smaller, this number's getting bigger. Okay, so far so straightforward. But then we are asked to do some organic chemistry. And the question takes a little bit of a bizarre turn with this rather strange bit about tartrazine being used to investigate the insides of mice. Read that yourself. Assume the total volume of aqueous region in a mouse's skin is 8.5 centimeters cubed. Calculate the minimum mass of tartrazine required to make this mouse's skin transparent. So we have a molecular mass and a volume. So we're going to need a concentration. All right, and so the concentration is here. All right, and it's related by this constant to the change in refractive index that we want to achieve. So we've got the refractive index that we have and the one that we want to achieve. So very simply, our delta n is going to be 1.45 minus 1.33 which is 0.12. So that's the refractive index change that we need to get, and that is then related to the concentration of the tartrazine by this equation. So I can write in here 0.12 equals 0.143 CT, and I can calculate CT is equal to 0.12 divided by 0.143, which is 0.839. The units, well, the units I am told are moles per decimeter cubed. So I need a concentration of 0.839 moles per decimeter cubed. That's great. And I am told that I have a total volume of 8.5 centimeters cubed. So in order to work out the number of moles that I need, and then the number of moles will give me the mass. So I'm going to do moles equals concentration multiplied by volume. So the concentration I have is 0.839, and then the volume I have is 8.5. Now that is in centimeters cubed, whereas my concentration is in decimeters cubed. So it's just a standard divide by 1,000. And that's the second volume unit conversion that we've had to do in this year's paper. And both of them very straightforward. Really not anything tricky at all. So I'm going to multiply that by 8.5 divided by 1,000, which gives me 0.00713. Always good to write out your working and any intermediate values you get, just in case you don't get the final answer. There might be some extra marks to pick up. So now my mass required is going to be my moles I've just calculated, multiplied by the molar mass, which is, I'm given here, 534.4. So I'm just going to multiply that by 534.4 to give me 3.81 grams. Okay, so now we have the organic part. Okay, and like I said, the previous question number 3, had a little bit of organic chemistry with the Passerini reaction, which was a lot of fun, but not really any synthesis. This is the main synthetic part, and there's only 1, 2, 3, 4, 5, 6, 7, 8 marks available for organic synthesis. So for the fans of organic synthesis, not much to go on this year. So we've got to find A, B, C, D, E, F. Okay, very straightforward. This first one here, you're given this benzene ring with a nitro group on it. They could quite easily have asked you to make this from benzene. I think that was a question last year, where you were given you start with benzene and then you added nitric acid and sulfuric acid together. But we do have the reduction here. So this should be fairly familiar, but even if you don't know this reaction, you are very generously given the molecular formula of this one, which I thought was also very, very generous. So I can see here that this is C6, and I've got 1, 2, 3, 4, 5 hydrogens. My nitrogen is still here, so I've lost my 2 oxygens and I've added 2 hydrogens. Couldn't be simpler. Okay, so we can go ahead and just put that one in. Okay, then we add this concentrated sulfuric acid. Now I'm not going to go through. I don't want to sort of get too much into the the nitty-gritty mechanistic details, as it were. Talk about the reaction in all the depth. I'm more interested in how can you do it if you're not familiar with the reactions based on the information that you're given in the question. So this one, we're given lots of molecular formulas. So here, what has changed? Well, I've still got 6 carbons, I've still got 7 hydrogens, I've still got my nitrogen, but I've got this SO3 here. Okay, now if I go down to here, I can see that my benzene ring, this benzene ring here, has got nitrogen. So that nitrogen is going to be this nitrogen here. And I can see that over here I've got the SO3. So I can see straight away which carbon I'm adding the sulfur group to. Okay, and there's also another one over here. So something's being done twice, and you can see here I get C, I do some stuff to C, and then I add in another C. So this first C here is going to be this one, and I'm going to add another C to the thing that I make. Fine. So it should be fairly clear that I don't do anything to the NH2. Now it says I have the same number of hydrogens, so I've removed the hydrogen there, but I add it back on because I have SO3H. Now the final structure here is the ion with the sodium counter ion, but that's going to be done in the last step. So up until the last step, we can assume that this whole thing here isn't going to change, and it's all the way through. It's going to be SOOOH all the way through. Okay. Then we are given NaNO2 and HCl. It's also really important. It's quite a lot of students. They write a formula out and they don't check that the thing they've written matches the molecular formula they're given. So, for example, a lot of students will have looked here and they've seen like, oh well, okay, it's SO3 minus. All right, and they'll go ahead and they'll draw here SO3 minus. And they won't then count, 2 hydrogens, 3, 4, 5, 6, and they're missing the 7th one here. So it's just really important as a final check, always double check that the thing that you've drawn matches the molecular formula that you've given. C, we then have C6H5N2O3S. And again, this thing here, that's not changing. We've still got it down here, so that's not changing. So the chemistry now is going to be happening at this end of the molecule here in order for us to be able to do whatever this is going on down here. So I have C6H5, so I've lost 2 hydrogens, which I can assume is going to be these 2 hydrogens, because there's no other groups anywhere else in the ring, and I've gained a nitrogen. So we're going to have our SO3H, and then we're going to have N, and that is going to be bonded to the other nitrogens, because you can see down here I have this NN bond here. Now there are, how many hydrogens did it say there were? There were 5 hydrogens altogether. So we've got 1, 2, 3, 4, 5. So we've used up all our hydrogens, which means that this is going to be a triple bond. Now this nitrogen here is perfectly happy. It's got 3 bonds. Nitrogen likes to make 3 bonds. This nitrogen has got 4 bonds. So the positive charge is going to be on that nitrogen. That's just something that you should be fairly comfortable with. For example, if you take ammonia and you make the ammonium ion by adding H+, you get NH4+, which is nitrogen with 4 bonds. So if I've got a nitrogen atom with 4 bonds, it's going to have a positive charge on it. So that is my positive ion, and then I got my Cl minus counter ion. Don't forget to put that on as well, and then double check that that matches my molecular formula. Then we have this Na2SO3, which we are told down here is a reducing agent very generously. So we then have C6H8N2O3S. Again, remember that is not going to be changing, and I then have 3 more hydrogens essentially. So I'm just going to add 3 hydrogens to this thing. So that's not going to change. And I'm going to get N, and I'm going to put 3 hydrogens on it. Okay, easy. 1 there, 2 there, and now both of those nitrogens have got 3 bonds. Okay, so now we get, so I feel like those first 4, they're not, I mean the first one's easy, and the first one's easy. B, C and D, a little bit more tricky, but not impossible. Then D is when it starts to get, what's D? D to E is when it starts to get a little bit more hairy. So what we're doing now is we're going to be doing this bit of chemistry down here. So we need to think very carefully about what's going on, and we're no longer given molecular formulas, but we should be able to look here, and you can see that I've got 1, 2, 3, 4 carbons in a row that are coming onto the benzene ring reactant that I've already got. And if I look at this here, I can see that I've got 2 carbons here in a row. That's not really going to help me. 2 carbons here in a row. That's not going to help me. But I've got 1, 2, 3, 4 carbons in a row here. So this new bit here is the middle section of this molecule. Now, what's going to happen is the 2 nitrogens, so these 2 nitrogens here, are going to react with 2 of these carbonyls. And we can think, well, it could either be, actually there's 3 possibilities, so it could be that 1 nitrogen reacts with this one nitrogen reacts with this one. Or it could be 1 nitrogen reacts with this one reacts with this one. Or it could be this one and this one. So in the final product you can see that there are 1, 2, 3 carbons. Okay, so which means that it must be that the nitrogens are reacting with this one and with this one, because they are 1, 2, 3 carbons apart. If it was to react here, you'd get a 4-membered ring. If it was to react here and here, you get a 6-membered ring. So by reacting here and here, you get this 5-membered ring. Okay, so what's probably the best approach here is to go ahead and start drawing the kind of thing that we're expecting to get, like it's drawn here. So I'm going to draw my benzene ring first. I've still got my SO3H. I'm not going to change that to a negative ion, because the negative, again, this bit here is going to come from the final step. All right, so I'm going to leave my hydrogen on. Then I'm going to get N. And now I'm going to draw my 5-membered ring. Like that. And I'm going to put on the OH, and I'm going to put on the carbonyl there. All right, so this carbon and the carbonyl group is this one here. Okay, so I'm then going to draw on the O and the ethyl bit on the end, because there's no reason for this to have come off. Now that clue comes from, you're told that you lose water and you lose ethanol. Now the ethanol you lose is this bit. Okay, because that's not here, that's turned into an alcohol group there. All right, there's no extra chain here. This chain then, because otherwise it would be -2 here. This chain isn't in the final product, but it is going to still be an E, otherwise that would have to be a 2. Okay, so then we have to work out what the specific structure of this ring is. Now my temptation is just to look at what they've got in the final product. Okay, so they've got a double bond here, and a double bond here. Now what I can do is I can sort of think to myself, well, does that mean, if I have this, obviously if you know the reaction you can work it out, right? But let's assume that we don't know what the reaction is. Can we work it out from this information here? Well, I had 3 hydrogens here. One of those hydrogens is going to go onto the ethanol when this oxygen comes off. One of them is going to go onto there, which means in order to lose the water, I need to lose another hydrogen from somewhere else. And that's being lost from this carbon here, because this carbon here, this one here, is this one here in the original product. Okay, so these are the same carbons. Here, this carbon has got 2 hydrogens. Here, it's only got 1 hydrogen, which then that gives me enough hydrogens to be able to lose the water. That's a pretty hand-wavy way of doing it. You might want to, if that was a little bit too fast, it wasn't quite clear, you might want to rewind and just listen to that bit again. But I think it works. Then we have compound C comes in again. So obviously compound C, this bit here now, compound C is going to be this bit coming in. So what I'm going to do is, at this point you can just work backwards. So you can think to yourself, all right, well, what is the sodium hydroxide going to do? So the sodium hydroxide is going to deprotonate this group, and you get a sodium ion, It's going to deprotonate this group, and you're going to get sodium ion. So all I need to do is just basically draw this, but just add on the hydrogen here, add on the hydrogen here, and it's going to hydrolyze this ester. Okay, so I'm going to draw it in like this. Okay, SO3H. I'm not going to change any of this bit. That bit. OH. And then, let's see. Okay, so that bit's still there. So this will be hydrolyzed by the addition of the base. And then I'm going to add on N. Be really careful about the connectivity. All right, just like that. Okay. The temptation is to sort of, lose this bit off here, and it's difficult if you don't, because we're not given the molecular formula. But I feel like this year, most of it's you can work it out, right, by either working forwards from the molecular formulas or working backwards and look at the reagents. But that is what you get, and then final step, that's going to come off, that's going to come off, and that's going to be broken down. So, next, we are then asked about this UV vis spectroscopy. So, suggest the colour of substance X based on its UV vis spectrum above. Now, rather annoyingly, I don't have a physical copy of the datasheet, which has got the colour wheel on it. But I've prepared my own version of the colour wheel. So if I look at the spectrum, I can see that I'm absorbing this low wavelength light and I'm absorbing this high wavelength light, and I've got this region here from about 350 to 500 where no light is being absorbed. All right, so all of this here is the light that's not being absorbed, so it's going to be this colour, because if it's absorbing all of this light, you're not going to see any of those wavelengths of light. You're only going to see these wavelengths, and those wavelengths of light correspond to a violet, indigo, blue. All right, so there are more than one colour. This is violet, this is indigo, and this is blue. But our options are blue, yellow, orange, and red. So it's obviously just going to be the blue colour. Okay. The way the colour wheel works is you can look at the wavelength that's being absorbed, and then the colour that you see is on the opposite side. So, for example, if I'm absorbing here at about 580, 590, if I'm absorbing this colour, then the colour that I see is on the opposite side, so it would be this colour here that I see. That's why it's put into a wheel, just because that's a nice little way of using it. So this is the one that's absorbed, and then the complementary colour, the one that you see, is over here. Okay, and then we have this question, which is a very, very interesting question. I didn't have a chance to do the whole paper. I had to go at a few of the questions. When I saw this, I didn't really know what was going on. I did it. I got it completely wrong, and then I looked at the mark scheme, and I still was scratching my head for a little while before I really worked out what was going on. I think I've worked out how to solve it, or at least like how they would expect you to solve it. So we'll have a little look at it. The first thing you'll want to do is read this, okay, very carefully, just to get your head around what's going on. And then there's a few interesting things for us to think about, right? So we're told we have a pH indicator. It's very easy to start making assumptions, like, oh, well, if it's a universal indicator, then I can say, well, whatever colour this is, and I can use that to try and solve the question. You're not told what kind of indicator it is. So the actual wavelengths that we're getting here are irrelevant. The colours are irrelevant. We can't make any conclusions about what the colours are. which is what confused me. I was thinking to myself, well, you know, if it's, let's say, suppose it's universal indicator, what colour would this be, what colour would this be, and so on, and then try to work it out from there based on the, you know, what's going on here. But I don't think that's really a possible way of doing this question. So what I'm going to do is I'm going to try and go through and make sense of all of this information here. So I'm told that I have a sample containing tartrazine, beta-carotene, the pH indicator, and it's all added to diethyl ether. So I'm going to have my tartrazine and my beta-carotene are going to be in my mixture. Okay. Hydrochloric acid is added, the mixture is shaken, and the layers are left to separate. If you're not familiar with the experimental technique that they're talking about here, it can be quite confusing. Essentially what they're going to do is they've got these two compounds and they've got an organic solvent, diethyl ether, and they've got an aqueous solvent, water with hydrochloric acid. They're going to put it into a separating funnel, which is a piece of equipment that you might have used or seen that looks like this. Okay, so you shake it up and then you let it settle, and what you do is you get two layers based on the, because obviously the organic layer and the aqueous layer will be immiscible, and you're then going to have the separation with the order based on density. So normally this will be your organic layer up here, and this will be your aqueous layer here. Now, based on the structures of these two compounds, we can assume that beta-carotene is going to be in the organic layer, and that the tartrazine is going to be in the aqueous layer, because it's got these ionic groups on that are going to be very attracted to the water. No such luck for beta-carotene, so that will be dissolved by the organic solvent. So let's go back down to here. It's my schematic diagram. I'm told then that the aqueous layer gives spectrum number 1, so I'm going to give that number 1, and the organic layer gives me spectrum number 2. Okay, fine. Then a base is added to the organic layer, so that's pretty much it for the aqueous part. So the organic layer, a base is added, which causes a colour change. Okay, so that's, I'm going to add my base, and then I'm going to take spectrum number 3. Okay, fine. Then the diethyl ether is evaporated from the organic layer, and ethanol is added to the residue. Any undissolved solids were filtered off and dissolved in hexane. So the ethanol solution gives spectrum 4. So this gets a little bit complicated. So I'm going to go down here, and I'm going to remove the diethyl ether, and I'm going to add ethanol. And that's going to give me spectrum number 4. But anything that doesn't dissolve in the ethanol is going to be dissolved into hexane, and that's going to give me spectrum number 5. Okay, so what this is doing is we are getting 2, 3, 4 is the sort of the separation and purification of our organic one. So we should be able to see that we have a sort of progression of similar spectra that get sort of cleaner, as it were. All right. The aqueous layer is going to be something different, and then hexane will be, well, we can think about that in a moment. So let's just look for 3 spectrums, and this is the part that I didn't really, that just completely went over my head when I did it the first time, is looking to look at the shapes of these. So it's now that I know I need to look at the shapes, it's obvious, right? I can see that this, and this are all similar. Okay, so those are going to be my 2, 3, and 4. Okay, which now makes it quite easy, because immediately this is going to be my sort of impure one at the start. So I think that's going to be number 2. This is going to be my pure one at the end. So that's going to be number 4. Well, no, sorry, I think I made a mistake. Let's just go back. Yeah, so what was down here I think I said the wrong thing. I think I said 2, 3, 4. Hexane is the organic solvent. So remember, the beta-carotene is going to dissolve into this layer. So 2 is going to be my beta-carotene. Then 3 is going to be the beta-carotene with the base. And then 5 is where my beta-carotene is going to end up. That's going to be my pure beta-carotene. So this one here. So this is, you can see here, this is my beta-carotene peak. And this is my impurity. So I'm removing that through this whole process. And you can see here, it's gone. So that's number 5. Sorry, that is going to be confusing. I'm not going to, I could go back and record the whole video, but we're already 40 minutes in. I mean, if you've made it this far, congratulations. Sorry that I sort of got a little bit mixed up here. Obviously, this is an organic solvent. This is going to be that's going to be getting your aqueous impurities out. So it's going to be 2, 3, 5. Yeah, sorry if that was confusing you. If you spotted the mistake that I made, well done. And so then what's going on here? Well, if this is obviously going to be number 3, because it's the only one left over with this peak in. This is the color change, right? So these two things here, these two ones are very, very similar, but this is the one where you get the color change. So that's when you add the base, is going to give you this big color change here by having that extra equivalent sized peak is going to change the color of it. And now you can see that this here has this peak at 600, which is this here, just sort of like zoomed in more. All right, so that is the bit that we remove off at the end. Okay, so that's going to be number 4, which means that this is number 1. Okay, so that's our tartrazine. All right. Okay, yeah, I think that's the only way of working out that that's number 4 and that's number 1. Yeah. Okay. Like I said, really tricky question. That took me, a bit of time, and I feel like in the actual test, reading this, working out all of this stuff, that's it's a long time to spend on a question, especially if you don't really know much about the technique. But hopefully that makes sense. If it doesn't make sense, maybe watch it again. If it still doesn't make sense, you can ask in the comments, and I can sort of have another go at it. But I think that's more or less the way it works. So that is the end of the question. Like I said, big question.